Okay, we have a few more examples of evaluating, and then I'm going to show an additional example of evaluating where we come up with an approximation. So all of these over here on the left, let's take a look at first. The cube root of 8. Remember, we're asking a question. The question is, what to the third power is 8? The answer is 2, because 2 cubed is 8. 2 times 2 times 2 is 8. How about this, though? If we throw a negative in there, what to the third power is negative 8? And is that or is that not possible? Well, if you consider numbers that are multiplied by themselves a certain number of times, you can come up with something negative. For example, a negative times a negative times a negative will be negative. If you just do a negative times a negative, that's positive. If you do it 4 times, a negative times a negative times a negative times a negative, that comes out positive, because remember, every time you multiply 2 negatives, you get a positive. So in this case, the cubed root of negative 8 is negative 2, because negative 2 times negative 2 times negative 2 is negative 8. And I'll write that one down. It would look like this if I were to check it out. Negative 2 in the parentheses, which comes out to negative 2 times negative 2 times negative 2, which indeed, these two negatives make a positive, but then I have an additional negative there, so the product of all three of them comes out to a negative value, negative 8. So if the root is a cube root or a fifth root or any odd numbered root, then it turns out you can come up with a negative, because an odd number of negatives being multiplied produces a negative number. Consider the square root of 16 next. The square root of 16 is 4, because 4 squared equals 16. But what about the square root of negative 16? What times itself produces negative 16? 4 times 4 is positive 16. Negative 4 times negative 4 is positive 16. So, what do we say about this? Well, we could say a couple things. We could say that this is simply not a real number. Okay. Not real. But it turns out that there is a solution to this. If your course uses the imaginary unit, then I could say that the square root of negative 16, is equal to 4i. So it looks just like this one, but I got to stick the I on there, because if you recall, I squared is equal to negative 1. This is a definition. The imaginary number is equal to the square root of negative 1. If you square that, it comes out to negative 1. And so if I were to check this solution, I would say, what is 4i, that quantity, squared? Well, it comes out to 4i times 4i, which is 16. I times I is I squared, and we just pointed out that I squared is equal to negative 1, so this is 16 times negative 1, which is negative 16. And so it checks out, only if you use the imaginary unit there. If your course isn't using the imaginary unit, then you'll just stick with this answer right there. It's simply not real. You cannot multiply 2 real numbers to get negative there. Moreover, you couldn't multiply 4 real numbers to get a negative number. So it does get a little bit more complicated with higher order roots, meaning that the index is higher and you have a negative number on the inside. Higher and even, I should say. The odd numbered roots that have a negative inside are pretty straightforward. So let me move on from talking about this to mentioning at least one example of approximating. And so let me see if I can squeeze this in somewhere over here. What if I had the, let's just say, instead of the cube root of 8, we had the cube root of 16. So the question is, what times what times what is 16? Well, 2 times 2 times 2 is 8, so it's not 2. 3 times 3 times 3 is 27, so we're somewhere between 2 and 3, but not exactly either one of those. Now, there is a way to approximate this. There are, as I mentioned before, many methods historically, but for now, let's just punch this up in the calculator. When you do that, this one comes out to approximately 2.52. Whenever you're having to round a number or truncate decimals, you know you're talking about an approximate value, not an exact value. So let me point that out. And you're probably asking yourself, how did I stick that into the calculator? Well, it depends what kind of calculator you're using. Some of the fancy scientific calculators that I like have buttons that look like this. There's a little box, and then a root, and then a box. So there's a clear place where you're going to stick in the index and stick in the radicand. And the way that my calculator works is I would put the index here and the radicand here, and what that's telling the calculator to do is stick that guy right there, stick this guy in there, and evaluate it. If you have an older calculator but still with some capability, you might put it in as a fractional exponent. So it's kind of interesting. It turns out that you can also do this, perform this evaluation by entering in 16 to the 1/3 power in your calculator. Now, how did I get that going from a root to a fraction? Well, let me just give you one quick definition. It turns out that the root, the nth root, I'll put it in green, the nth root of r to the, we'll say p for some power, is the same as r to the p divided by n, the power divided by the index. Now this is kind of a fancy definition, and where did I get 1/3 out of this using this definition? Well, in this case, 16 is to the 1 power. I'm doing root of 16 to the 1 power, and you see the 3 on the outside, and hence 1/3. And I could give another example of that, and why don't I do that? Let me erase some of this here. I'll give one or two more examples of how this works. But for now, I'm really just trying to get at the way to approximate it using your calculator. Which is kind of funny, isn't it? A new blend of reason and technology to somehow achieve understanding. What are the philosophical implications? I don't know. Maybe it's always been like that. I don't know. I like to wax on while I'm waxing the glass here. That is cleaning it. Blah, blah, blah. Could pause the video, but then you don't get to see me doing all this. And that's really exciting, so I didn't want you to miss out. Okay. Here's another example. Let me point this definition out again. I kind of like jumped into definitions, went kind of speedy ahead, it looks like. But suppose we had this one, the 4th power of 3 to the 4th, which we previously talked about. And of course, what to the 4th power is 3 to the 4th? The answer is 3. We already know the answer. And it's clear, but I just wanted to point out how this definition also fits. I could say that this is equal to 3 to the 4 divided by 4 power, using this fraction as the exponent to represent the root. 4 divided by 4 is 1, so this gives me 3 to the 1st power, and anything to the 1st power is itself. So indeed, it works. Let me also show you another one that is clear that you're used to. Suppose we did the square root of 16. Okay, we know that comes out to 4. I'll just put that right here. 4 times 4 is 16. And that is the principal root. But if I represent this using this fractional exponent kind of thing, I could look at it a couple ways. I could say, oh, the square root of 16 is the same as the square root of 4 squared. Remember, there's a 2 right here, even though it's not typically written. So this would be the same as, just like the example above, 4 to the 2 divided by 2 power, which is 4 to the 1, which is 4. But what if you took 16 all the way down to its prime factorization? What if instead of the root of 16, you were looking at the root of 2 to the 4th power? 2 times 2 times 2 times 2, all prime numbers, is 16. That's the prime factorization of 16. And remember, there's a 2 out here. Again, all I'm doing with this is trying to illustrate the fractional exponent way of representing a root. Okay, so then this would be 2 to the 4 divided by 2 power. This one, the inside divided by the outside, 4 divided by 2. Which is, 4 divided by 2 is 2, so this is 2 squared, which is 4. So indeed, this method of representing the root by the fractional exponent is a solid way to do it, and a nice way to approximate if you don't have this fancy button from your fancy scientific calculator. Maybe you've got this one in your older calculator, or can somehow do it that way. Okay, let me move on to the next video, and I will start to show you how to simplify roots that are not exact, kind of like this one, the cube root of 16, which approximates to 2.52, but suppose we wanted an exact, not an approximate answer, quote unquote simplified in the math world. I will show you how to do that on the next video.